Hi, my name is Marc Rosen, and I'm going to be discussing Balboa, which is a new framework and implementation for network censorship circumvention. This work was done with my co-authors, James Parker and Alex Malozemoff. Oppressive regimes are increasingly using internet censorship as a tool to suppress human rights. In 2020, 56% of global internet users lived in countries where political, social, or religious content was blocked online. In response to this, researchers have spent the last several decades working on new censorship circumvention techniques. The Balboa framework represents our contribution to this body of work. With Balboa, we focus specifically on the link obfuscation part of censorship circumvention. In this setting, we have two parties, A and B, which want to communicate with each other across the internet. The censor has full access to the network and can both passively observe as well as actively manipulate network traffic. It will shut down any connections that it suspects are attempting to circumvent its censorship policy. Of course, the censor could just block all network access entirely, and this would certainly disrupt the communication between our two parties. However, we assume that there is at least some traffic which the censor does not want to block. Specifically, we assume that the censor wants the pink machines to be able to communicate using some approved communication protocol. If we can make the communication between our parties A and B look exactly like the communication between the censor-approved machines, then the censor won't be able to block the communication between A and B without also blocking the communication between the pink machines. Let's say that the communication between the pink machines is encrypted so that the censor cannot see the contents of their communication. Unfortunately, encryption alone won't allow parties A and B to trick the censor. Encryption only protects the contents of messages, not any of their metadata, including size and timing. As a result, unless the metadata of A and B's communication exactly matches the metadata of the communication between the pink machines, the censor will be able to distinguish between them and block just A and B's communication. For the next few examples, let's say that the pink machine is running Skype and that the censor has approved this protocol and won't block it. One approach to make the traffic between A and B look like Skype traffic between the pink machines would be to write code to generate network traffic, which would have the same metadata characteristics as real encrypted Skype traffic. This approach is called Mimicry, and it's the approach taken by systems such as Skype-Morph. Unfortunately, as the Parrot is Dead paper notes, practically implementing Mimicry approach is nearly impossible. Any mistake in the Mimicry implementation is a possible avenue for the censor to distinguish it from the standard implementation, which would allow the censor to block it. So if mimicking with code a target application is very difficult, what if we just ran the target application instead? This is called the tunneling approach, and it's the approach taken by censorship circumvention systems such as Delta Shaper. Delta Shaper runs a standard instance of Skype on the machines which want to communicate with each other. It then tunnels data through Skype by giving Skype a fake video feed which consists of the data it sends over the network. By running an actual instance of Skype, the tunneling approach solves many of the issues with the Mimicry design. Unfortunately, many systems that use tunneling, including Delta Shaper, are detectable by a censor because the non-standard input to the target application produces correspondingly non-standard network traffic. So in summary, we want to 1. Run a standard instance of the target application so that we don't fall into the pitfalls of Mimicry. Well, 2, using the standard input to the application so that we don't fall into the pitfalls of tunneling. But 3, we also need somewhere to put the covert data in the network stream. Balboa is a censorship circumvention framework which achieves these 3 goals. First, it runs an unmodified binary of a TLS-enabled target application so that we don't fall into the pitfalls of Mimicry. And 2, we run the application on its standard input so we don't fall into the pitfalls of tunneling. And third, Balboa inserts itself between the target application and the operating system. It then intercepts and manipulates the application's network stream to embed and extract covert data. Here's an overall architecture of the Balboa framework. We start with the target application, and we've instantiated the Balboa framework for both internet radio streaming and web browsing. On the server side, the target application produces network traffic, which the Balboa framework intercepts to modify and rewrite in order to embed covert data in it. The updated network traffic is then sent to the operating system, which sends the data through the network and through the active adversary over to the client. On the client side, the same process is used to manipulate an incoming connection to embed and extract covert data. The Balboa framework itself is made up of several components. First, we intercept and manipulate the target application's TCP stream via dynamic library injection. The intercepted stream is fed through the TLS rewriter, which decrypts and re-encrypts the layer of TLS encryption. Lastly, we have the traffic model. The traffic model is a parser which identifies, in the plain text network stream, places where we can embed covert data. In order to instantiate the Balboa framework in a new setting, all that's needed is to write a traffic model that's appropriate for the new setting. We've written a traffic model for the internet radio setting, in which an internet radio server streams OGG Vorbis audio data to clients. In order to avoid changing network metadata, the traffic model's modifications are length preserving. We say that the internet radio server and client have already agreed on the music that we'll be playing. At the moment, this is done by pre-sharing the audio file, though the server and client could, for example, communicate a seed which would be used to generate the audio. For authenticated Balboa clients, the internet radio server will embed covert data into the TLS encrypted audio stream. For each outgoing OGG page, if its audio data is contained within the pre-shared audio data, the server will replace the contents of the OGG page with covert data. It will then replace a deterministic field in the OGG page metadata with the position in the pre-shared audio file that the original OGG page's contents came from. The media player client will then extract the covert data and undo all of the changes to the OGG page. After Balboa has finished this client-side processing, the OGG page is sent to the media player. This final OGG page is identical to the one that was originally created by the internet radio server. This process yields efficient data transfer. 98% of the bytes sent over the wire can be rewritten to transmit covert data using this approach. Importantly, the target application, not Balboa, is responsible for determining the network footprint of the system. In addition, because covert data is handled inside the traffic model and not the target application, the network footprint is independent of the communication patterns of the covert data. In order to make its network footprint as close to the target applications as possible, Balboa intercepts network streams via dynamic library injection. Dynamic library injection is a feature of the dynamic linker on many operating systems. It allows you to override the definitions of functions that a program calls. For our purposes, Balboa uses dynamic library injection to override the functions in the C standard library which are used to manipulate network sockets. For example, we override the connect function so that when the target application wants to connect to an IP address and port, we can flag the resulting file descriptor as being one that we want to manipulate. By overriding the write function, we can manipulate the outgoing data immediately before the operating system sees it. Because our dynamic library injection always preserves the lengths of buffers that it encounters, and also does not change any socket options on the socket, network manipulations made with this dynamic library injection approach should be undetectable by the sensor, provided that the buffer rewriting operation is fast enough, and that the sensor can't detect the changes that were made to the buffer's contents. Importantly, this technique does not depend on the internals of the target application, as long as it uses libc's system call wrappers, or on the internals of the target application's TLS library. Though the dynamic library injection in Balboa is completely agnostic to the internals of the target application's TLS library, in order to decrypt the contents of the TLS stream, Balboa needs to be able to somehow extract the TLS keys. To do this, we take advantage of a standard debugging option present in most popular TLS libraries called SSL keylog file. Enabling this option will cause the TLS library to dump the TLS master secret key to a file. The Balboa TLS rewriter can read this file to decrypt and perform surgical manipulations on the TLS stream. Importantly, using the SSL keylog file means that Balboa does not modify the TLS handshake in order to learn the TLS keys. Sensors place heavy emphasis on the TLS handshake to try to detect censorship circumvention attempts, and Balboa is entirely immune to these attacks. Beyond passive handshake observation attacks, practical sensors also attempt so-called active probes of servers, in which they make requests to a server to see if it's being used for censorship circumvention. In order to pass this check, a Balboa-enabled server must respond to these probes in the same way that a normal server would respond. The Balboa TLS rewriter employs a custom covert signaling protocol to mutually authenticate the client and the server in order to figure out on which network connections it's communicating with Balboa clients. It will rewrite these connections while leaving the other connections untouched. After the TLS rewriter takes care of covert signaling, its job is to decrypt the TLS stream, giving the plaintext stream to the traffic model. It then receives a modified plaintext stream from the traffic model, which it re-encrypts. To evaluate Balboa's security, first note that 1. Balboa only modifies data which is indistinguishable from randomness to the adversary, And 2, because of Balboa's use of dynamic library injection, it preserves all socket options and all lengths of all buffers that are sent to and from the operating system. As a result, the only way in which Balboa's network footprint can diverge from the network footprint of the target application is in the timing of the rewriting that Balboa performs on network buffers. To evaluate whether Balboa has the same network footprint as the target application, we collected packet captures from runs of the target application with Balboa enabled and runs with Balboa disabled. We then extracted TCP statistics from these packet captures and trained a random forest classifier to distinguish between these scenarios. Because we have perfectly clean training data, this represents a worst-case scenario for Balboa. For the internet radio scenario, we have a single codebase which can be injected into several media players. As a result, it's easy to change the network footprint of Balboa by simply swapping the media player that it's being injected into. Looking at these results, we can see that the classifier failed to detect Balboa with any great accuracy across several media players, even in this worst-case scenario. In addition, the accuracy sharply drops when even a little bit of latency is added. This evidence suggests that Balboa's network footprint is extremely hard to distinguish from the network footprint of the underlying media player. Similarly, for the web browsing instantiation of Balboa, the classifier cannot detect Balboa with high accuracy. We're excited about the Balboa censorship circumvention framework and the possibility of extending it to even more scenarios. Please see our open source implementation on GitHub and feel free to email us with any questions.